A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
Think about the last time you were on a long-haul flight, maybe crossing the Atlantic or heading into a major hub like Tel Aviv or New York. You were sitting there, the engines throttle back, the flaps extend, and then you feel that solid thump as the wheels make contact. To most passengers, that is just the end of the journey, a signal to start unbuckling and reaching for their phones. But from an engineering perspective, that moment is essentially a controlled mini-collision. We are talking about hundreds of tons of metal and fuel dropping out of the sky and slamming into the earth at 150 miles per hour. Today's prompt from Daniel is about the structural integrity of international airport runways and the physics of landing massive aircraft on surfaces as unconventional as solid ice.
It is a phenomenal topic because we often treat the ground as a static, given thing. We look at the airplane, we look at the jet engines, we look at the avionics, but the runway is arguably one of the most over-engineered structures on the planet. I am Herman Poppleberry, and I have spent way too much time looking at pavement classification numbers this week. When you have a fully loaded Airbus A380 coming in at 560 tons, you're talking about a hammer strike that would pulverize standard highway asphalt in a matter of days. If you drove a semi-truck onto a runway, it would be like a toy car on a marble floor. The forces involved are just on a different order of magnitude.
I remember seeing a slow-motion video of an A380 landing gear during touchdown. The way those tires smoke and the struts compress is incredible. It looks like the whole plane is trying to bury itself in the ground. But you mentioned pavement classification numbers. I assume there is a specific language engineers use to talk about whether a runway can actually handle that hammer strike.
There is a very specific system called the Pavement Classification Number, or PCN. It works in tandem with the Aircraft Classification Number, which is the ACN. This is the international gold standard managed by the International Civil Aviation Organization. The basic rule of thumb for airport operations is that the ACN of the plane must be lower than or equal to the PCN of the runway. But it is not just a single number. A PCN is actually a 5-part code. It tells you the load carrying capacity, the pavement type, whether it is rigid or flexible, the subgrade strength, the maximum tire pressure the surface can accept, and how the value was even calculated.
So it is like a secret handshake between the plane and the pavement. If the plane's handshake is too aggressive for the pavement's grip, you have a problem.
If you try to land a heavy cargo 747 on a strip designed for small regional jets, you aren't just going to get some surface cracks. You risk a catastrophic subgrade failure where the actual earth beneath the pavement gives way. Imagine the landing gear strut acting like a giant hole punch, snapping through the concrete and sinking into the dirt. That is how you lose an entire airframe and shut down a hub for weeks.
So it is not just about the thickness of the concrete on top. It is about the entire geological stack underneath. We aren't just talking about a sidewalk here.
Not even close. A modern international runway is a multi-layer cake, often 6 to 8 feet deep. At the very bottom, you have the subgrade, which is the natural soil. But you can't just build on whatever dirt is there. It has to be incredibly compacted and often chemically stabilized using lime or cement to change the soil's molecular structure and prevent it from shifting with moisture. On top of that, you have a subbase of crushed stone, then a base course, and finally the surface layer. That surface layer is usually one of two things: flexible pavement, which is asphalt, or rigid pavement, which is high-strength concrete.
I have always wondered why some airports seem to prefer one over the other. If you go to a lot of major American hubs, you see those big concrete slabs with the expansion joints that give you that rhythmic thump-thump when you're taxiing. But then other places are smooth asphalt. What is the trade-off?
It usually comes down to the frequency of traffic versus the ease of maintenance, or what engineers call life cycle cost analysis. Rigid concrete pavement is much more durable over the long term. It distributes the load over a much wider area of the subgrade because the slab acts like a giant bridge. It can last 25 to 30 years before needing a total overhaul. The downside is that when it does fail, or if a slab cracks, the repair is a major operation. You can't just patch concrete and land a plane on it an hour later. It needs time to cure and reach its design strength.
Whereas asphalt is more like a quick fix.
In a way, but a very sophisticated one. Asphalt is flexible, meaning it deforms slightly under the weight of the aircraft and then recovers. It is much faster to repair. You can mill off the top couple of inches and repave it overnight, and it is ready for the morning rush. But asphalt is prone to something called rutting, where the heavy wheels literally push the pavement into grooves over time, especially in hot climates. If you have a line of heavy jets waiting to take off on a 100-degree day, they are basically kneading the runway like dough.
That makes me think of the recent work at Heathrow. I was reading that in their 2025 and early 2026 runway reconstruction projects, they have been moving toward these very specific polymer-modified bitumens. They aren't just using standard road tar. They are essentially engineering a plastic-infused binder that can handle the thermal expansion of a London summer without getting soft enough for a 747 to leave permanent footprints in the runway.
That polymer modification is the cutting edge right now. It allows the asphalt to maintain its elasticity across a much wider temperature range. But even with the best materials, the physics of the landing gear is what really saves the runway. If an A380 had only 2 wheels, it would punch straight through the concrete like a needle through paper. Instead, it has 22 wheels. By spreading those 560 tons across 22 contact points, the actual pressure exerted on any single square inch of the pavement is kept within a range that the structural stack can handle. It is all about load distribution.
It is the same principle as a snowshoe, just on a much more massive scale. But how do they know when the internal structure is starting to fatigue? You can't exactly dig a hole in the middle of a busy runway at O'Hare to see if the subbase is holding up.
They use something called a falling weight deflectometer, or FWD. It is a specialized trailer that drops a large weight onto the pavement and uses sensors to measure how much the ground deflects in microns. By analyzing those microdeflections, engineers can calculate the structural stiffness of the layers underneath without ever breaking the surface. They can literally see a subgrade failure starting to form months or years before a crack ever appears on the top. It is like an ultrasound for the Earth.
That is the part that fascinates me. We talk about safety in aviation mostly in terms of the planes, but the monitoring of the ground is just as rigorous. If a runway loses its friction rating because of rubber buildup from tires, they have to come in with high-pressure water jets or chemical solvents to strip that rubber off. If they don't, a rainy day turns that mini collision into a hydroplaning disaster.
The rubber buildup is a massive logistical headache. Every time a plane lands, the tires have to accelerate from 0 to 150 miles per hour in a split second. That friction leaves kilograms of rubber on the surface in a single go. Over a few months, that fills in the macro texture of the pavement, which is what provides the grip. But let's shift gears a bit, because Daniel's prompt also touched on something that seems to defy all this rigid engineering: landing on ice.
Right. We have all seen those videos of C-17 Globemasters, or even civilian research planes touching down in Antarctica. To the average person, ice is something that cracks when you step on it wrong. How does a 200-ton military transport not just vanish into the ocean?
It comes down to the distinction between standard frozen water and what engineers call blue ice. In places like Antarctica, specifically at sites like the Pegasus White Ice Runway or the newer Phoenix Field, they are utilizing ice that has been compressed over thousands of years. As the snow is buried, the air bubbles are squeezed out and the density increases until it reaches about 0.9 grams per cubic centimeter. For comparison, normal ice is much less dense and full of air.
So this isn't the kind of ice you find on a lake in Minnesota. This is more like a rock formation made of frozen water.
Precisely. Blue ice has a structural bearing capacity that rivals some forms of concrete, but the engineering required to maintain it is actually more intense than a standard tarmac runway. In Antarctica, they have to use specialized grooming equipment to keep the surface at a specific level of roughness. If it is too smooth, the planes can't stop. If it is too rough, the vibration will shake the airframe to pieces. They actually use a process called proof rolling, where they drive incredibly heavy rollers over the ice to see if it deflects. If the ice holds up to the roller, it will hold up to the C-17.
I remember we touched on some of the survival logistics at the South Pole back in episode 1250, but the actual runway physics is a different beast. If you are landing a C-17 on the ice, you have to calculate the ice-to-weight ratio constantly. The ice isn't just a surface, it is a floating or grounded slab that flexes. If the temperature rises by just a few degrees, the structural integrity changes completely.
And that brings us to the most difficult part of ice operations, which is the guidance systems. Daniel asked about instrument landing systems, or ILS, on ice. On a permanent runway, an ILS involves fixed antennas at the end of the strip that beam a very precise radio signal to the plane to help it find the glide slope. But on a glacier or an ice shelf, the ground is moving.
It is literally a slow-motion conveyor belt. You can't just bolt an antenna into the ice and expect it to be in the same place 6 months later.
You can't. The ice might move 30 or 40 meters a year, so for Operation Deep Freeze and other major polar missions, they use what is called a Deployable Instrument Landing System, or DILS. These are mobile units housed in towable trailers that can be recalibrated and physically moved to account for the glacial drift. They also rely heavily on differential GPS, where a base station on a known fixed point, like a nearby mountain peak, provides corrections to the aircraft's satellite navigation, giving them centimeter-level accuracy.
That is wild. You are landing on a moving sheet of ice using a mobile radio tower, and you're doing it in a plane that was designed in the 50s or 60s, like we discussed in episode 1016. It really shows the versatility of those airframes. But back to the ice itself. Is there a limit to how many times you can land on it? Tarmac wears out, but ice melts or shifts.
The fatigue life of an ice runway is measured by its thermal budget. Every time a plane lands, the friction of the tires and the heat from the engines transfer energy into the ice. If you have too many landings in a short window, you can actually start to degrade the surface density through a process called ablation, or even subsurface melting.
So you literally have to let the runway cool down.
In some cases, yes. And in the summer months in Antarctica, many of these runways have to shut down entirely because the subsurface temperatures get high enough that the ice loses its structural rigidity. It is the ultimate seasonal infrastructure. You build it, you use it for a few months, and then the environment basically reclaims it until the next winter cycle.
It makes me appreciate the sheer permanence of something like the runways at Ben Gurion or JFK. They are designed to be forgotten in a way. You only notice a runway when it is bad. When it is good, it is just an invisible stage for the aircraft. But as we move toward the future, I have been seeing more about smart runways. We aren't just talking about better concrete anymore.
We are moving toward embedded sensors. There are projects now using fiber optic cables embedded directly into the runway layers during construction. These cables use something called distributed acoustic sensing. By sending light pulses through the fiber, the system can detect the vibrations of every single aircraft and calculate the exact stress being placed on different sections of the runway in real time. It can even tell if a plane is overweight or if its tires are unevenly pressurized.
That would take the guesswork out of the falling weight deflectometer tests. Instead of checking once a year, you have a continuous stream of data telling you that, hey, the third slab after the touchdown zone is starting to show microfractures.
And that leads to the next step, which is self-healing materials. There is research into capsules of epoxy or even specific bacteria like Bacillus pseudofarmus embedded in the concrete. When a crack forms, the capsule breaks or the bacteria are exposed to moisture and they produce limestone to seal the crack before it can spread. It sounds like science fiction, but when you consider the cost of shutting down a major runway for even 6 hours, the return on investment on self-healing concrete is actually very high.
It is the difference between a minor maintenance cost and a billion-dollar logistical nightmare. I think that is the big takeaway for me. A runway isn't just a road. It is a dynamic structural system that is constantly being monitored, tested, and stressed to its absolute limit. Whether it is the high-tech polymer asphalt of a major international hub or the ancient blue ice of the Antarctic, the engineering is about managing that mini collision in a way that the passenger never even has to think about.
It is the ultimate invisible success of civil engineering. If the runway does its job, nobody says a word. If it fails by even a few inches, the whole world hears about it. I find it fascinating that we have reached a point where we can land a 500-ton machine on a piece of frozen water and have it be a routine, safe operation.
It really puts things in perspective when you're sitting in 32B complaining that your peanuts are salty. Meanwhile, the ground beneath you is performing a structural miracle.
A miracle of compaction and load distribution. I think we should also mention the role of autonomous maintenance. We are starting to see drones equipped with high-resolution cameras and LiDAR that can scan a 4,000-meter runway in minutes, looking for foreign object debris, or FOD. Even a single bolt left on the runway can be sucked into a jet engine and cause a catastrophe.
The Concorde disaster is the haunting example of that. A small strip of metal from another plane led to the loss of the entire aircraft. So the engineering isn't just about the strength of the ground, it is about the pristine nature of the surface.
The level of precision is just staggering. From the chemical composition of the bitumen to the satellite-corrected glide slopes on a moving glacier, it is all about narrowing the margin of error to near zero.
Well, I think we have thoroughly deconstructed the ground beneath our feet. It is a lot more complex than just flat pavement.
It usually is when you start digging, literally and figuratively.
Before we wrap up, I want to point people toward a couple of related episodes, if they want to keep pulling on this thread. If you are interested in the visual side of how pilots actually find these runways, especially in bad weather, check out episode 438, where we decoded airport lighting systems. It is the perfect companion to the structural side we talked about today.
And if the ice runway part of the discussion grabbed you, go back to episode 1250. We go much deeper into the actual survival logistics of living in Antarctica, which puts the difficulty of maintaining those blue ice runways into a whole different context.
Also, episode 1016 on why 70-year-old planes still fly is a great look at the airframes that have to survive these landings for decades.
It all connects. The plane, the lights, and the pavement.
Big thanks to our producer, Hilbert Flumingtop, for keeping the show on the rails. And a huge thank you to Modal for providing the GPU credits that power our research and generation pipeline. This has been My Weird Prompts.
If you found this interesting, the best thing you can do is leave us a review on Apple Podcasts or Spotify. It genuinely helps more than you might think in getting the show in front of new people.
You can find all our past episodes and ways to subscribe at myweirdprompts.com. We will be back soon with another deep dive.
See you then.
Take care.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from sloth, from man, from long-eared host. My Weird Prompts, until next time, stay curious, keep